The name of our project is MEUS, a framework for the management of emergencies through ubiquitous sensing, which aims at proposing a solution to handle the aftermath of a natural disaster like an earthquake. Hereafter, I'm going to present and describe how we have broken down the problem and we have proposed a framework to achieve a better understanding of the specific search and rescue scenario ahead of a similar real-world case. Here in the image above is an aerial image from the Italian town of Amatrice, when back in 2016 it has been affected by an earthquake. The main purpose in this scenario is to conduct the operations so that citizens in danger are promptly rescued according to the gravity of their condition. In order to achieve that, we believe that a data exchange procedure has to be devised, so that first responders as well as citizens should be able to share useful information so that the help is delivered as quickly as possible, knowing the level of urgency and the location of where to lead the rescue. The possible hurdles to achieve such objectives are that the huge amount of data that has to be collected in order in such a scenario, the difficulty of reaching certain areas, as well the lack of internet connection. So we have wondered why, not why, but how we can tackle these problems. We believe by the exploitation of a mobile application used by first responders as well as citizens, used to share information, to communicate among them, as well as to send the information and the observation collected in the environment to a remote database in the cloud, which is used to store the information and process it, so to guide first responders to the correct path. So as well, of crucial importance can be the deployment of unmanned aerial vehicles, drones, namely, which can help improve the search and rescue operations. So in order to act at full capacity and speed in a real-world case, we thought a proper framework had to be devised in order to test different situations and assess how to act under specific conditions, as well as to test the scalability of the approach. The simulator has been developed with the aim of testing the information exchange mechanism in the environment. For this reason, we decided to implement it in Python, exploiting OSM&X, which is a Python package to download spatial data from OpenStreetMap with real-world street networks. Once the graph of a specified location has been fetched, then it is projected to the UTM coordinates for the UTM zone in which the graph's centroid lies. Coherently with the model, each graph node contains the following relevant information, which are the position in the environment expressed both in latitude and in longitude, and in UTM coordinates, as well as the event that can be observed in that node and the global connection availability in that node, if there is the coverage or not. For what concerns the agents, some of the most relevant features are the global connection, can be, for instance, on mobile devices, the 4G, the 5G, or Wi-Fi, or short-range connection like Bluetooth, Zigbee, or Z-Wave, and a list of information elements. List of information elements is an entity we're going to describe in the next slide. Eventually, the remote database to store the information elements is implemented as a relational database in the cloud using Flask, RESTful, Marshmallow, and SQL Alchemy. So for what concerns the data management, we propose a model which could enable us to easily reconstruct the graph for each observation made in the environment by an agent. To achieve the formation objective, the local database of an agent has been organized into what we define as information element. Through context-free grammar, the information element has been modeled as illustrated in the slide. It cannot happen that at the same observation exchange, thanks to this design, we can easily perform our algorithm, and it cannot happen that the same observation is exchanged multiple times between the same agents in different nodes at different times. So here we have even an example of an information element from when we see that we are able to construct the graph from which the information has traveled so far. So here we showcase the result. Here we see two different images in which we have mainly tuned two parameters, which are the number of gateways agents, which are the agents able to send the information to the remote database, and the radius, the amplitude of the radius of the internet connection coverage. So we see that to reach the same number of observations, as we increase these parameters, the time required to perform the experiment decreases. So we think this is our validation for our system.